Hello everyone, my name is Renata Castelo Branco and I'll be presenting Visual Meets Textual, a hybrid programming environment for algorithmic design, a joint work with António Leitão. Algorithmic design is a method increasingly present in the architectural practice, which entails the creation of designs through algorithms or computer programs. Algorithmic design, or AD for short, has been having a great impact on the optimization of projects, which becomes particularly relevant in the complex geometric buildings of contemporary architecture, like the ones you're seeing here. They would all be rather hard to both model and build with conventional design approaches. The idea behind AD is that instead of us building the digital model manually, we can instead build a program that builds the digital model for us. And we have two main paradigms to do this. Besides the typical textual programming logic used in computation, there is the visual paradigm, which is very dear in architecture since it is closer to the visual nature of our profession. Here you have two examples. On the left, Grasshopper, grabbing and dropping components onto the canvas, and on the right, Kepri, defining functions in a textual programming language. These two paradigms present very different sets of advantages and disadvantages. Visual programming languages are easier to grasp because they allow us to work with concrete instances, and the code-model relation is also more explicit. But they lack abstraction mechanisms, which hinders proper scaling with complexity. There's a lot of repetition involved at large scales, and we end up using textual scripts to solve the problem anyway. Textual programming languages, on the other hand, scale better with larger programming projects, precisely because they allow for abstraction, although that is also the reason why they entail a steeper learning curve. So a third paradigm was created that attempted to join the best of both worlds, the hybrid programming paradigm. There are examples of this, for instance, PIM, or Programming in the Model, by Malachy and Woodbury, or the Mobius Modeler by Jensen and Associates. The problem is that despite all these promising advantages, it seems that the hybrid paradigm has not yet sparked the interest of this community, at least not in large scales. The podium in that regard clearly belongs to visual programming. So we decided to take a shot by creating a hybrid solution on top of an already widely used visual programming tool, Grasshopper, coupling it not only with an easy-to-use textual language, but also with an existing AD tool to try and help users progress from one to the other. Our textual AD tool is Kepri. It uses the Julia programming language, a textual programming language for sure, but an easy one that is not too verbose, and it is very similar to the mathematical notation. Kepri communicates with several backends, modeling tools like CADs, beams, but also analysis tools and game engines, and the hybrid system can access any of these. Grasshopper, on the other hand, is integrated in Rhino. Now, this is not to say that it can't communicate with other tools. It can via plugins, but this essentially means that we need to use different components to generate geometry in different tools, which is very different from Kepri's approach, where the same operation generates equivalent geometry in all backends. In Grasshopper, we can also write scripts in textual programming languages when the existing components aren't just enough for the job. But there is nothing hybrid about this. If we want to use them, we have to go learn these languages somewhere else, which in the case of C# is not exactly easy. There is also no progression from here. We're stuck to using these languages as a complement for Grasshopper components, since they have little other representation in architecture and other AD tools, Python being the one exception. It is a lot easier to learn, and it is used in other AD tools. The implementation of Kepri GH is in itself many ways similar to these scripting editors. For instance, you go and grab the little bug from the Math tab as well. You drag the component onto the canvas, or you can also look it up on the search engine. And by double-clicking on it, it opens the editor box where users can develop Julia code within. But the code can also be accessed in a textual programming editor. As we shall see, this is a lot nicer because we have syntax highlighting. In order to illustrate the changes the hybrid system would introduce to a typical Grasshopper workflow, we define these four main programming phases or tasks where the differences become visible. In a typical Grasshopper workflow, we have, for instance, in the first row, program visualization, which is transversal to all others. We use the Grasshopper canvas to visualize our program throughout the whole process. Phase 1 includes calculations, mathematical functions, mapping of locations, for instance, all of which are typically done using Grasshopper components. Abstract computations are recursive and iterative procedures, or higher order functions, typically implemented with the aid of textual scripts. Geometry generation is usually done with native components, which then provide feedback in Rhinoceros. Some changes are introduced with the Kepri workflow. For instance, We can still do program visualization in the Grasshopper environment, but now we also have the possibility to visualize the textual part of our program in a dedicated textual environment. Phase 1 can be done using Grasshopper or Capri components, Phase 2 mostly using Capri components, and Phase 3 forcefully using Capri components if the geometry is to be portable amongst backends. Here's an example. I am creating a Mobius strip component. You see the inputs and outputs defined by major and minor signs. And my component is, first of all, producing a matrix of locations, which I'm now converting into something that Grasshopper can read, just to show you that we can mix Grasshopper and Capri components and use Grasshopper to generate geometry as well if we want. But more interestingly, I can use sliders, for instance, to manipulate the dimensions of my Mobius strips. I can use a Rhino point to dislocate my surface throughout the space. And now I want to move on to Capri backends like AutoCAD. And since I'm going to use Capri backends, I can use just Capri operations. And there is one particularly important in this case, which is a surface grid. And the surface grid receives the matrix of points directly from my component, and I don't need all that complication for Grasshopper. As you see, the sliders work just in the same way for the AutoCAD backend and for the Unity backend as well, which is another one of Capri's backends. In this case, it's a game engine. Now, I'm doing something a little bit more interesting, which is abstracting this Mobius strip function. I've just copied it to the more general definitions component, so I don't have to repeat these definitions. And I want to do a function that will allow me not just to do a Mobius strip, but for instance, a sinusoidal surface or a Dini surface. And for that, you will see that I have added another parameter, an f parameter, to my new function, the parametric surf. And that f parameter is the name of the function itself that I want to use. And now, as my new component has also another f input, I can just give it in the name of the function written in a Grasshopper panel. It works properly for the Mobius strip, as you saw, and now I'm testing it out with new values for the Dini surface. The sliders work pretty fast. And last but not least, I'm just testing it out with a sinusoidal function. There we go, sinusoid function, creating a surface. So I also want to illustrate Capri GH's features with a more complex case study, a more architectonic one too. This is a project for a nautical center in Lisbon, a building projected onto the Tagus River, which is divided in 3 main blocks anchored at the pier, which are then interconnected by 2 other volumes lifted up in the air above the boat ramps. And within this concept, most of the parameters, geometrical constraints, are variable. As you see here, in this animation, we're changing the volume's width, length, height. We're also changing the ramp's width, arch curvature, truss section. Everything is parametric. Here's the program that originated this model, and I'm going to use it to show you some of the features of the system, namely traceability. As I click on any of Capri's components, it immediately highlights the geometry that it generated in the backend. In this case, you're seeing the model generated in AutoCAD. I will also show you immediate feedback, which is the ability to recompute the model after any change in the program. In this case, I'm changing parameters using the sliders. And I'm showing you also that this is a little slow in the hidden mode of AutoCAD, but it's faster, for instance, in 2D wireframe. You have to remember that we are generating geometry, so it's not like the Grasshopper preview. It's more similar to baking geometry in Rhino. I'm also showing you the options that you have for editing code, so this box editor here. And I'm also showing you, while I'm at it, that some of the components here pretty much use the same function, right? The Capri base. There's a lot of repetition within them. They're making the same geometry. So what I do is essentially extract the definitions that I think I will be repeating throughout my program into this huge component, the definitions component, that feeds all others. And of course, for this component, I prefer to use the dedicated textual editor because it has a lot of definitions and it's just easier to see them with syntax highlighting. This is something that is quite different from the previous scripts that we saw in Grasshopper, as we're really trying to avoid repetition, so that whenever I have a mistake in my program, I can just go and correct it in one place and not be constantly having to change it in 100 places. I've shifted on to another backend, which is Unity, and I am showing you that it is a bit faster than AutoCAD's 3D mode at generating geometry, as you would expect from a game engine. But Well, yeah, I'll just show you another thing, which is traceability. As you'd expect, these features work similarly in all of Kepri's backends. So if you click on any component, you'll see the corresponding geometry highlighted in the model. Last but not least, the question just then becomes, where should one draw the line between visual and textual? Or in this case, where should users shift from using Grasshopper components to Kepri components, relinquishing the ease of use for computational power, and if this is somehow related to one's programming capabilities? And we believe so. We think that expert programmers, expert Grasshopper programmers, will likely be more willing to use Grasshopper components throughout, maybe just use Kepri components for abstract scripting as a last resort. And as long as they do the geometry generation using Kepri components, they can still benefit from portability amongst backends, and that's fine. On the other hand, experienced textual programmers will probably use more Kepri components from the start in all phases, although they're still benefiting from the visual environment all the way throughout their design process. And we would just like to leave you with this idea of transition, which is what a hybrid approach should motivate. The system can work as a bridge between visual and textual. On the one hand, helping users that are already experienced in Grasshopper transition to the textual paradigm smoothly and in an environment that they feel comfortable using. And also for textual programmers who want to use a more user-friendly visual programming environment to program their designs. So that's all. I hope I got you interested in hybrid programming, and if you want to know more, get in touch.